Algebra 3, Chapter 1, Section 8, Other Types of Inequalities. We're going to learn about polynomial inequalities and solving them algebraically first. To solve a polynomial inequality algebraically, what we need to do is get the polynomial in standard form equal to 0. Then we're going to factor the polynomial and solve for x as if it were really an equation. We're going to make a number line and mark the values of x on a number line. Now what this will do is it's going to divide our number line into regions. So these values are going to put walls up on our number line, put boundaries up. We're going to test points in each region of the number line, and we're going to see where the numbers are that satisfy the inequality, because if one number works, every number in that particular region will work, and if it doesn't, none of them will. Now graphically, a little bit different. What we do graphically is we get the polynomial again in standard form with 0 on the right-hand side of the inequality. We graph the left-hand side. We could put that in our calculators as y1, and we examine the graph. If the inequality is a less than, then we're looking for x values where the graph dips below the x-axis, and we write down the intervals of x values where that occurs. If the inequality is a greater than, then we're going to look for the x values that occur where the graph lies above the x-axis and write down the range of values for those. There are some unusual solution sets we need to be aware of. And this is the first one. The solution set for this is all real numbers, because no matter what number you put in here, it will solve this inequality. It will satisfy it. There is no number you can put in here that will not make this true. So this is a set. The solution for this is the set of all real numbers. Okay, this one, well, when you factor, you get a solution set of x equals -1. And when you check the points on each side, well, none of them satisfy the inequality, which means that -1 is the only solution. So instead of a range of values, which is what we usually have, we actually only have one value where this works. And here we have our third. When you graph this, you'll see that there are no solutions to this inequality at all, because this entire graph lies above the x-axis. And the inequality is asking for where the x values are that where the graph lies below the x-axis. And then finally, factoring this gives you a solution of 2. Well, when you check the points on each side, all of them satisfy the inequality except 2, because it's not a greater than or equal to 0. So the solution set is all real numbers except 2. Now, rational inequalities. We solve these algebraically in a very similar manner to the polynomial inequalities. We get the rational expression on the left side of the inequality and 0 on the right. Then what you want to do is you want to make sure you only have one rational expression. So if you have fractions that are being added or subtracted, make sure you find common denominators and combine them so you just have one fraction on the left side. Then what you want to do is factor both the numerator and denominator, and you want to set each of these factors equal to 0 and solve for x. Then you're going to take those numbers, put them on the number line just like we did with the polynomial inequalities, and that's going to divide the number line up into regions, and you will check a number in each region to see which numbers will satisfy the inequality. Be sure to consider the fact that we don't want to have a 0 denominator. We can't have a 0 denominator when we're writing the final answer. So you do have to think a little bit more about the rational inequalities, but overall the solving process is very similar. So we have x squared is less than 9. We're going to subtract the 9 from both sides so that we have a 0 on the right. We're going to factor and solve, so we get x equals 3 and x equals -3. Then we're going to put those points on our number line. And this is dividing our number line up into 3 segments. The first segment is from negative infinity to negative 3. The second is from negative 3 to positive 3. And the third goes from 3 to positive infinity. And then we're going to test a number in each of those 3 sections to see where the numbers lie that make x squared is less than 9 true. So we tried negative 5, and that didn't work. We tried 0, and that did work. And then we tried positive 5, and this didn't work. So the numbers that will work for this inequality are the numbers that lie between negative 3 and 3. So our solution is negative 3 is less than x, which is less than 3. Now you try this problem. Pause the recording, give it a try, and resume the recording to check your answer. Now we did need to multiply out the left-hand side because we have to have a 0 on the right-hand side. So we multiplied it out, we used FOIL, and then we subtracted the 25 from both sides, and then we factored. And once we did that, we were able to find our 2 solutions for where this equals 0 are negative 7 and positive 3. So we put those on the number line. And again, our graph is divided into 3 regions. We're then going to test a point in each region to see which numbers make the inequality true. Once again, we're discovering that the middle section is the section that works. This will not always be the case, so don't assume that it will be for every problem. However, it is for this one. The numbers between negative 7 and 3 satisfy the inequality, so our solution is negative 7 is less than x, which is less than 3. Here's a rational expression. Give this a try, pause the recording, resume the recording to check your answer. Okay, the top and bottom here don't need to be factored. They can't be factored. So we just set each part equal to 0, and we get 2 solutions. We get 5/3 and we get 5. And even though 5 would give us a 0 denominator, we're still going to use it to try to help find the numbers that will work. So we're going to put both of these on our number line. And then we're going to, again, test a point in each region for the 3 regions that are created when we put the points on the number line. So we'll try 0, and that worked. That made it true. Then we tried 2. 2 did not work. And then we tried 6, and 6 did work. So we have 2 regions this time that work. Now, here's where we need to be careful. It looks like our answer is going to be x is less than or equal to 5/3, or x is greater than or equal to 5. However, we don't want x equal to 5, or we will have a 0 denominator. So our solution is x is less than or equal to 5/3, or x is greater than 5. We need to leave the equality off of that because we do not want a 0 denominator. This one is going to need to be factored. Factor the numerator and denominator. Give this problem a try, pause the recording, then resume the recording to check your answer. So here we have the factored form, and we're going to set each of these factors. We have 4 factors: x, x plus 2, x plus 3, and x minus 3. And all of them get set equal to 0 and solved. So we have 0, negative 2, 3, and negative 3. And we do put all of those onto our number line. And we're going to have a little more testing to do, and we're going to have to use a fraction in there for the between negative 3 and negative 2. So here's all of our testing. Okay, we used negative 4, then we used negative 2.5, we used negative 1, we used 1, and then we used 4. And notice that there are 2 regions that work here. We had 5 total. So the numbers between negative 2 and negative 3 worked, and the numbers between 0 and 3 worked. Now again, we cannot include the 3 or negative 3 as part of the answer, so we need to watch how we write these. We're going to have negative 3 is less than x, which is less than or equal to 2, and 0 is less than or equal to x, which is less than 3. Again, we leave the equal off when it comes to the 3 and negative 3 because those would both give us a 0 denominator. Okay, same idea with this one. What you want to do is you want to get a 0 on the right side, and so you're going to need to subtract the 1 over x minus 3 from both sides. Why don't you pause the recording, give this a try, and then resume the recording to check your answer. Okay, here we subtracted it. Now we need a common denominator. And our common denominator is going to be x plus 5 times x minus 3. And then we need to multiply that out, combine like terms. And notice that I didn't multiply the denominator out. It was already factored, and I need it factored, so I don't want to do double the work. The top, once I combine like terms, does not need to be factored. So I have x minus 11. X plus 5 and x minus 3, which gives me 11, negative 5, and 3. Again, I'm going to put those on my number line. I have 4 regions to check, and I'm going to check all 4 of them. And it turns out that my solution is between negative 5 and 3 and greater than 11. Now this time I didn't need to worry about the 0 denominator because it was strictly greater than problem, so it didn't have an equal to, and that made it a little bit easier. You may have noticed by now that most of the time we have kind of an every other pattern in the regions that work. That does occasionally, occasionally that's not the case, but usually you do see where it's every other section that's going to work. Okay, give this example a try. Now be careful. Not only do you need to combine these fractions, but you need to move the 1 over also. And you've got to get it into all one fraction on the left side. So pause the recording, give it a try, and resume the recording to check your answer. Okay, here we move the 1 over. We gave everything the common denominator of x minus 1 times x plus 1, including the 1. Here we've combined it into one fraction, multiplied and FOILed, and combined like terms. Now the top will not factor, and if you try using the quadratic formula of completing the square, you're going to get imaginary results. And we can't put imaginary results on a number line, so we only need to worry about 1 and negative 1. Now we're going to test a number in each region. And we find that the numbers up to negative 1 and the numbers after positive 1 will work. So our solution is x is less than negative 1 or x is greater than positive 1. Okay, here's an application problem. A rectangular playing field with a perimeter of 100 meters is to have an area of at least 500 square meters. Within what bounds must the length of the rectangle lie? Okay, if you want to try this on your own, go ahead and pause the recording and then resume it to check your answer. First of all, we know that the perimeter is twice the length plus twice the width, and it is 100 meters. So we know that. Which means if we divide everything by 2, the length plus the width must be 50. And we can use that to solve for one of the variables. In this case, we solved for w. W equals 50 minus L. We also know that the area has to be at least 500 square meters. So length times width, which is the area of a rectangle, has to be greater than or equal to 500. So we're going to substitute 50 minus L in place of width in this inequality. And we get 50L minus L squared is greater than or equal to 500. Negative L squared plus 50L minus 500 is greater than or equal to 0. And you know we don't like to have that negative up front, so we multiply everything by negative 1. But when we multiply an inequality, when we multiply both sides by a negative number, we must reverse the inequality symbol. So now we have L squared minus 50L plus 500 is less than or equal to 0. When we graph we see that the length of the field must be between 13.8 and 36.2 meters.